Okay, welcome back. We are again looking at the Rosemount Model 3144P, the temperature transmitter. We previously looked at thermocouples. Now we're looking at RTDs. So our thermocouple, we used a 1/2 inch NPT fitting with stainless steel, about 2-inch long probe of a thermocouple. This time we're using an 1/8 inch and the probe is about 3 inches long. The length does not matter because the sensing portion is at the tip. Okay, so if anybody is wondering why was that one so much bigger than the RTD, I have RTDs that actually look identical to this one, which is a thermocouple, except you have 3 wires instead of 2, and obviously they're color coded differently. So although these look different physically, we're not worried about the outer look of it because a thermocouple and RTD can look exactly identical on the outside. We have to look at the wires, and we can tell that this one is a thermocouple because we have a red and a yellow. And if we want to know for sure whether it's a thermocouple and RTD, we can measure the resistance across here because we know that a thermocouple is only 2 wires put together of a dissimilar metal. Therefore, the resistance is going to be 0. However, it is going to mess with your meter a little bit, and you will get about an ohm of resistance. With an RTD, we should have, if it's a platinum 100 ohm, we will have 100 ohms at 0 degrees, and at 20 degrees, we'll have about 110 ohms. Now, we're going to be using a 3-wire RTD. So this is our little RTD, and it's going to come over here, and it's got 3 wires. And I've already took the liberty of hooking it up so that I could use 2 hands. Now, as we look at this, we see that 3 wires. We have the compensation line on 2 and 3, and we have the other lead on 1. Now, if we measured between 1 and 2 with our meter, now, of course, disconnected from the transmitter, because the transmitter will give you some weird readings. Disconnect it from the transmitter. If you went from 1 and 2, you would get 110 ohms. If you went from 1 and 3, of course, it's disconnected, not measuring the transmitter, measuring the RTD. You went from 1 to 3, you would get 110 ohms. And from 2 and 3, you might get an ohm, because that depends on your lead wire length. Now, we hook this up as per our hookup. Now we have to, of course, change our entire setup because we were sourcing thermocouple type K, and our transmitter is set up for thermocouple. So we have to go, and sorry, I was not looking at the screen, I was looking at the communicator itself. We're going to go into the guided setup again, and we're going to configure the sensor. We're going to go to sensor 1. We're going to go all the way up to platinum 100 with an A or alpha or coefficient of 385. Now that's not actually 385, that's 0.0385. That's what it's actually saying. Now you see we have a pt100 391, 3916. You want to know what your RTD is. Most of the time it's a 385, but make sure that when you order an RTD or when you pick up an RTD, it's a 385. So we're going to enter that. Now, how would we know that the one that we have here is a 385? Well, the only way to know is that I ordered it that way. So by looking at it, we would have no idea. But I know that I ordered it that way, so that's what I have. And in industry, most of the time we use a 385. Okay, and we're not using a 2-wire, we're using a 3-wire. The advanced settings are all going to be the same, so I'm going to finish. And then I'm going to exit. Now I'm going to go back to my overview. Okay, it's saying it's 24 degrees. Let me grab this RTD here. And I am warmer than 24 degrees. Looks like I'm still alive. So we're at 27 and we're still driving up. You can see by the milliamp output. I can hit that button there. There we're over 28 degrees Celsius, and that's because I'm holding it. So as soon as I put that down, of course, my temperature is still going up because it's still, my hand heated up that mass of metal, and so it continues to rise until that mass of metal starts to cool again, which now it is starting to cool again. It takes a couple seconds. And so now it'll start going down and down and down. It's always easier to inject heat than to remove heat. So it's going to take longer to go down than for it to go up. Now, how can we calibrate this? Again, we could stick this in an ice bath, but let's say that I'm at work, which I am right now, and I was up on the 10th floor or the 11th floor. Do I want to drag an ice bath up there? Okay, that wouldn't be so bad. But then what about the heat source? Now I have to take like a crock pot or a kettle or something up there to give me boiling water. That seems like a big hassle. So how could we do this so much easier? Well, the Fluke Precision Calibrator, the 276, we can also source resistance. So we need to source a 3-wire RTD. So here we go. We're going to remove our leads that we had previously. We're going to grab these leads. And again, going by our wiring diagram, 3-wire. We're going to hook our first one to terminal number 1. Our second wire into terminal number 2, and our third wire into terminal number 3. Okay, now we're going to take this. We tied our 2 black together because we can only source between 2 points. We can't source a 3-wire RTD by putting this lead over here. We can only source the resistance coming out of these 2 ports. So we have to have banana clips that can actually stack on top of each other. Now, that gives us our compensation. Now we have to set up our meter, and we press source. Well, we're already on source, so we'll just go RTD. So there's platinum 100 in degrees C, and we're reading 0. We are injecting 0 degrees at the moment. Now, in order to inject 0 degrees Celsius, we have to inject 100 ohms. However, once we start increasing, and let's say we go up to 100 degrees C, we have to put in a specific ohmic value. How do we do that? Well, the first thing we need to do is we need to get a chart. Now, as I said about data cards, if we have a data card, it tells us what our ohmic value is. Okay. Now, this specific transmitter was set up for -10 to 40, which would give 4 to 20 milliamp output. And so at our 0% minus 10, it was 96. At 40 degrees, it should be 115.4 ohms that we have to inject. Now, how do we do that? We can simply use this decade box. And if we say we want 100 degrees Celsius, 100 ohms to give us 0 degrees, we would set the decimal places to 0. And we would go 0 in the ones column, 0 in the tens column, and 1 in the 100 column. Now we have 100.00 ohms. And we would hook our leads into our low and our high. However, that is a little tedious compared to when you have the fluke calibrator. So now we're going to take a look at the fluke calibrator, what it can do. We have the fluke hooked up, and it is sourcing our degrees Celsius. It is reading our milliamp, and it's actually supplying our loop power. So we don't have any 24 volts going to this because it is supplying our 24 volts. Now, I don't need to know what the ohmic value is because I can just go 10 degrees. And our meter here reads 10.13 degrees Celsius. Now it is a hair high. Is it possible that the Rosemount is out or that I am inducing a little bit of air? Unfortunately, the correct answer is I am creating a little bit of air because it is outputting resistance, but I have not taken into account the resistance of my lead wires. So that is the downfall of doing it this way, sourcing by temperature. What I should do is I should measure every wire, take it into account, and then source by resistance based on the lead wire resistance. However, I'm not going to do that today because when we're talking 0.2 degrees Celsius, that is such a small margin of error, that we're going to let that go today. And we're going to look at the fact that I'm injecting by temperature. And so now I'm going to go to 50, just to move this along a little quicker. Now we're at 50 degrees Celsius. It's reading 50.2 degrees Celsius. And it's outputting, trying to output 12.03 milliamps, and I am reading 12.03 milliamps out. So my D to A converter is correct. Now if I go up to 100%, 100 degrees Celsius, which would be my 100%, I should get 20 degrees out, 20 milliamps out. Say these things enough times and they start getting jumbled. We are injecting 100 degrees Celsius. We are reading in our electronics 100.2 degrees Celsius. Our electronics are trying to drive 20.035 milliamps, and we are reading 20.03 milliamps. We are very, very close. So, is that in cal? It's very close. If we wanted to change something, again, we go to our service tools, we go down to maintenance, and we could go to our sensor calibration. We don't need to do an analog calibration because our D to A was perfect. Now, if we want to get closer and we want to really do a very thorough calibration, we would have checked the resistance of the wire. We would have went to an RTD table. We would have then subtracted that ohmic value of our leads from the RTD table, and we would have went to ohms. Ohms. Now, let's say, let's go to 100. Now, 100 ohms, that should give us 0 degrees. and we are reading 0.28. So let's see if we lower this a little. So if we lower it by 0.1 ohm, it goes to 0.00 degrees C and gives us a perfect 4.00 milliamps. And we are getting 4.00 milliamps. We can't get better than that. Now, is it possible that our leads are 0.1 ohm resistance? Pretty much guaranteed they are. So that was our error, was 0.1 ohms in our lead wires right here. So not only do we see how to easily calibrate it, you'll notice that you did have a 0.1% error because of that. So if you can live with 0.1% error, well, that's pretty good for most applications. If you need it closer, then I recommend sourcing ohms based upon the RTD table, subtracting your lead wire resistance, which if it's a short wire like this, it should only be like 0.1 ohm, 0.2, but measure it so that you know, and then you subtract it so that you get the proper readings. So all in all, we have now calibrated this Rosemount 3144P temperature transmitter, both in the thermocouple in the last video and now in a 3-wire RTD orientation setup. And both went extremely well. Now, if we were going to mount this transmitter, it has a mounting bolt in the back right here, and it gets mounted up, hopefully somewhere where we can actually get at it. And then all these wires here, they come out this port here in usually a liquid tight connection. Okay, or it might be a probe that actually seats right into there, and then that probe sticks right out. So I hope this video was informative. Please let me know what your thoughts were on the video, if it helped you out in any way. I hope seeing the fluke, being able to source and being able to read the milliamp output and being able to use the loop power, that you can see how great of a tool it is and how powerful of a tool it is and how great this 475 Hart communicator is. It's a lot better than the older versions. There's newer versions out even now, and they keep getting better and better, and hopefully we keep seeing more improvements. They did a great job on the Rosemount transmitter. So all in all, I love this transmitter. I think it's a great transmitter. Thank you very much for watching.